All right, so yesterday we were talking about solving equations by using the power property. Now, for the most part, that is whenever we have radicals involved. But there are some other cases where the power property comes in very nicely. Okay, so for example, if I ask us to solve the equation x to the 5 halves equals 243. Now, there we go. So this doesn't necessarily have a radical in the way that it's written, but it is kind of radical in nature. What we want to do is we want to be able to get rid of this power. So the power here is what's in our way. That's the thing that's stopping us from having x by itself. So the power property says that we can raise both sides of the equation to the same power. Now when we have radicals, you wanted the power to match the index, so they could cancel out, so to speak. Here, when you have a fraction for power, you want to raise both sides to the reciprocal power. So raise, in this case, both sides to the 2/5 power. Do that on the left, and do that on the right side as well. Remember, when you do a power to a power, you end up multiplying. And when you multiply a fraction times its reciprocal, you just get 1. So here we would have just x. And then on the right side, this is 243 to the 2/5 power. Now, in order for us to work this out, we need to remember certain things that we have about radicals. Now, we talked about this last week when we did a review for radicals, so it's a good idea to go ahead and bring it up again. When you have x to a rational power like this, x to the 1 over n, this can be translated as the nth root of x. Basically, the denominator of your power becomes the index of your radical. So if we have things that are a little bit more complicated, where we have something other than 1 for the numerator of that power, the best way to write this is the nth root of x all inside of parentheses raised to the m power. This is not the only way of working it out or thinking about it, but it is the best way, because in this form you would take the radical first, then you would apply the power. So basically you're taking your number and making it smaller before you make it bigger. You don't really want to go the other way where you make the number bigger just to make it smaller. You end up dealing with larger numbers than you really have to. So here, as we work this out, this means, look what we have here. The denominator becomes your index. So here, that denominator of 5 becomes the index of our radical. So this is the 5th root of 243. The numerator is the power to which we will raise that expression. So that's how we translate that rational power. So if you have your list of powers that I gave you earlier this semester, you just go down that list of 5th powers until you get to 243, and you see that the answer here is going to be 3. Okay, and again, just off to the side so that you know where this is coming from, we are saying that the 5th root of 243 equals 3 because 3 to the 5th power is equal to 243. Now, this example that I have for this connection between the base of 3, the power of 5, and the answer of 243, we're going to come back to this very shortly after we come back from our extended spring break. We're so used to doing radicals and thinking about the right process for that and knowing that we're trying to get 3, but later on we're going to be working on having the base of 3 and figuring out what the power is, and that's going to lead to logarithms. Really fun stuff as long as you've got your power sheet. Alright, so now we finished this problem. 3 squared is 9. Okay, not too bad. The big step is making sure that you raise both sides to the reciprocal power and understanding that this is not times 2 over 5, but that this becomes a radical. Your denominator becomes the index, and the numerator becomes the power. And so you do it one piece at a time. As soon as you start to say, oh, this is multiplication, then you're going to be in trouble. All right, let's try another example very similar to this one. Let's take the quantity 3x minus 7 raised to the 3/4 is equal to 16. Okay? So we don't want to have that power there. We're trying to get rid of the power so that we can have just the base left over. And so like we did in the last example, we want to get rid of that power, and we use the reciprocal to get rid of it. So I'm going to raise the left side here to the 4/3 power, which means I have to do the same thing to the other side. And again, this is an application of that power property. If you raise one side of an equation to a power, you've got to raise the other side to the same power. We're not just picking any random powers, we're picking ones that are going to be reciprocals of this. So these guys are going to reduce and simplify away, and we're left with the base. So 3x minus 7 equals, now we already know what's going to happen over here. We understand, well, this is not the problem I meant to do. That's okay. This means that we have the cube root of 16, and then this is raised to the 4th power. All right, so this might get a little bit messier than I expected, because I thought I had this planned well, but I did not. So let's work this guy off to the side, okay? So unfortunately, the cube root of 16 is not a perfect cube, so we're going to have to work with that guy. All right, so if I look at the cube root of 16, you know what, I'm going to do this. I'm going to rewrite this. So this was to the 4th power. I'm going to rewrite this. 16 is 2 to the 4th power. I'm going to take this index of 3, and I'm going to put that in the denominator. And then this is raised to the 4th power. I know it looks kind of weird, looks kind of crazy, but just go with me on this. Okay? This is going to keep us from dealing with a lot of big, nasty numbers. Okay? So 16, again, is not a perfect cube. But if I look at 16 as 2 to the 4th, and I take my index of 3 and make that the denominator, we have this expression. And when you have powers to powers, you multiply. So this becomes 2 to the 16/3 power, like that. Well, unfortunately, 16 does not divide by 3 nicely, but we can look at this and think about it as a mixed number, right? So off to the side, remember that 16/3 is the same thing as saying 5 1/3. So that means I can now split this up to say that this is 2 to the 5th power times 2 to the 1/3 power. Okay, and again, the reason for that is, think about what happens when you multiply. When you multiply, you would add the powers. And if you add 5 1/3, you get 16/3. So I'm just kind of splitting this up so that we can work with this a little bit better. 2 to the 5th, if you work that out, is going to be 32. And 2 to the 1/3 means the cube root of 2. So that's how all of that guy is going to simplify on the right side. Okay? So we have 3x minus 7 is equal to 32 times the cube root of 2. I mean, that's a real number. It's just not the prettiest number. And then we go through the rest of the process of getting x by itself. So for us, that just means adding 7 to both sides. Now understand that 7 and the radical don't get to go together, so they must remain separate. So 7 and a positive 32. Cube roots of 2. And then we finish by dividing everything here by 3. All right. So x is equal to 7 plus 32 cube roots of 2 all over 3. Okay? So I think the most difficult part was dealing with this radical over here. When I was making the problem, I thought I had it right in my head. This would have been a lot easier had the 16 been 8, and I think that's what I was thinking of. But you know how sometimes you have one number in your head, but then you write a different number? So sometimes that happens, but we still work through it anyway. We basically broke this 16 down in terms of its powers because, again, over here, 16 is 2 to the 4th. The index becomes the denominator. And then here it's an exercise in working with powers. When you multiply, when you raise a power to a power, you multiply, so you get 16 thirds. And then you just kind of keep going at it that way. Another way of looking at this, if you guys were ever in my 0310 class, take this 2 to the 16 thirds power and let's rewrite that. We can rewrite this as the cube root of 2 to the 16th. Now I want you to compare this to some problems that we would have had in another class. If I had written the cube root of x to the 16th, we know that the trick here is to divide 3 into 16, and that tells you how many factors of x could come out. So there would be 5 factors of x. So when you divide 3 into 16, you get 5 with a remainder of 1. Okay? So it looks like that. The same thing is happening here with the radical in the 2. 3 goes into 16 5 times, so every 3 factors of 2 will give you 1 on the outside. So by having 16 factors, you get 5 on the outside, and you're going to have one guy who's left over who doesn't have enough to break out. And that's the same stuff that we have over here. Okay, just written a little bit differently. All right, now please make note of this next problem that we're going to do, because in this next problem there's a bit of a trick, something that a lot of students tend to forget. I know every time I put it on a test, just forget one little piece of important information. If I take 2x plus 5, to the 2/3 is equal to 49. Again, we want to get rid of the power so that we can get to the expression on the inside. And again, just like in the last 2 examples, we're going to raise both sides to the reciprocal power. All right, so raise this to the reciprocal power, so that's going to be to the 3/2. Do it on the right side as well. Remember, what you do on one side, you do on the other side. So these guys are going to reduce away to give us a power of 1, and a power of 1 just means I get 2x plus 5 on the right, on the left. On the right side, the denominator tells you the index, so this means I'm dealing with the square root of 49, and I'm going to be raising that to the 3rd power. But here's where you have to make a little note. Okay, notice that this guy is even, so you have an even denominator for your power, which means that you are dealing with an even root, which means this guy is connected to that square root property, which means you're going to have 2 solutions, or 2 answers from here. Going to have 2 answers because we have to use that plus or minus. That's what we talked about at the beginning of this week. When we were using the square root property, when we are the ones putting the square root in the problem, a plus or minus has to come out, and that's exactly what's happening here. This even denominator indicates an even power. Whether it's a 2 or 4, if it's an even power that you are putting in there, you must also put in the plus or minus right here. Please, please, please do not forget that. A lot of times students, when they're doing their homework, they come to a problem like this and they go, I don't see why I'm getting this wrong because I know that I've got the right answer. There's another one to get. All right. So 2x plus 5 is equal to plus or minus, the square root of 49 is 7, raised to the third power. All right, if you look at the list of powers, we will find that 7 to the third is 343. Now, if you cube a positive, you get a positive. If you cube a negative, you also get a negative. So we still have the plus or minus showing up here. And now we just finished solving this for x. All right, so we subtract 5 on both sides. And really at this point, this is a nice linear equation. The only funny business that we have is with the plus or minus. But keep in mind that plus or minus is only connected to the 343, not the 5, not anything else. We divide both sides of the equation by 2. And we have x equals negative 5 plus or minus 343, all divided by 2. But we can't stop here. And the reason we can't stop is because we don't have anything radical, we don't have anything imaginary. And when that is the case, you have to separate and split up your answer into the two different possibilities, one with the plus and one with the minus. All right? So that means that x equals negative 5 plus 343 divided by 2, or we're going to need to figure out the other answer. X is equal to negative 5 minus 343 divided by 2. All right? So now let's just work these out. Negative 5 plus 343 is 338. Hopefully you guys are checking me today after the debacle that was yesterday. 338 divided by 2 is 169. And then we look at the other side here. Negative 5 minus 343 is negative 348 divided by 2, which gives us negative 174. All right? And again, you guys should be able to verify that those both of those answers do work when you plug them into the original equation. All right. Hopefully that's good. I know it was kind of messy there. We just have to make sure that we remember that when we are taking an even root, we put the plus or minus in here, which is going to lead us to, for the most part, 2 answers. Okay? And there we go. So that's going to finish up our discussion for using the power property. But the other thing that we had on our list today was to solve equations that are quadratic in nature. So that's what we want to look at right now. So what does it mean to be quadratic in nature? Well, quite simply, it means this. For an equation to be quadratic in nature, it is an equation that is not quadratic in and of itself, but it has these quadratic tendencies and these quadratic characteristics. So what we're going to do is we're going to write this. A u squared plus bu plus c is equal to 0. This is an equation that is quadratic in nature. Instead of having the x's, you have u, where u is going to represent some other variable expression. It could be something nice and simple like x squared. It could be something more complicated like a big fraction or a big expression like 3x minus 7. Okay? So let's just work through a nice little example of this and see how it can be. So for example, if I take x to the 4th minus 3x squared minus 28 is equal to 0. Now, you don't have the square, the x, and the constant like we're used to seeing, but we have things that are very close to that. For things that are quadratic in nature, you're going to have a constant here at the end. You're going to see something that's not quite x right here. Okay? And then you're going to see the same expression, but with double the power. And that's what you're going to see right here. And that's what makes this guy quadratic in nature. If you take this power and double it, you get x to the fourth. So you've got your constant, you've got a variable expression, and then you have that variable expression squared, which is again why I'm saying you have that power doubled. Now, if you look at the things that are done in the textbook or My Math Hub, they're going to say go ahead and do a substitution. But for something like this, we don't need to, because you already know how you're going to factor this guy, right? So x to the fourth should very easily break down as x squared times x squared. And we even saw an example of this last week when we were reviewing factoring. And now you're just trying to find factors of 28 to subtract to 3. And so those factors are 7 and 4. Paying attention to your signs, we're going to have a minus 7 and a plus 4. So we factor this just like any other factoring problem. Even though it's not quadratic, you can still factor it. And that's one of the things we're going to see a lot in these problems, is that we're going to manipulate them and rewrite them so that hopefully we can factor them. At this point, we now want to switch gears and do the zero factor theorem. The zero factor theorem would say, take each factor and set it equal to 0 and solve each of those smaller equations, like this. And if you look at them, I don't want you to be overwhelmed when you see this. I want you to be able to see just this guy right here, x squared minus 7. Okay, that's a nice little quadratic equation. This is the only place where you see your variable, which means we should use the square root property. So we're going to move the 7 to the other side of the equation, and we use the square root property. So even though this started off by factoring, we use the square root property to finish this. Now, notice again, I'm the one who's introducing the square root to the problem, so that guy is going to have a plus or minus. When we finish this, x is equal to plus or minus, and we can't do anything else with the square root, so we leave it as it is, the square root of 7. So right here we have two solutions, but notice that in the original equation it had a degree of 4. So we're supposed to get 2 more solutions. Well, we have another half that we need to worry about. Take this guy, and just like x squared minus 7, you want to solve this using the square root property. So x squared, move the 4 over, is equal to negative 4. Now to undo the square, take the square root of both sides like this. Don't forget the plus or minus. And x is equal to plus or minus. The square root of 4 is 2. And the negative inside leads to an I outside. So you can see that we have 4 solutions. 2 are real, although they are square roots, and then we have 2 that are imaginary. So 2 and 2 will give us the 4 total solutions we're supposed to have for this equation. Okay? So, if we can factor, great, and it makes it nice and easy. So let me show you what I mean by having to make a substitution. Okay, so let me take 5x plus 6 quantity squared minus 2 times 5x plus 6 minus 48 is equal to 0. Now there are a few different ways of handling this problem. I'm sure that I have some students who would like to go ahead and square this out and distribute the 2. But instead of doing that, here's what I want you to see. I want you to see that you have this expression 5x plus 6 not only in the middle, but you also have it right here for that leadoff part, and it is squared. So what we do is that we have something that's that's quadratic in nature. You've got your constant term, you've got your variable piece, and you've got the variable piece squared right here. So here's what we're going to do. We're going to do something that's very popular in math called a U substitution. And what that is that you use a different letter to represent a bigger expression like this. So we're going to let U equal 5x plus 6. So we're making a little transformation of sorts. And now we're going to rewrite the problem. So this is now going to be U, the square is still there, minus 2, and instead of 5x plus 6, we write U minus 48 equals 0. So we've kind of changed the way that this problem looks. Instead of having the 5x plus 6, which kind of complicates things, we now just have these little u's, and you treat them like a normal variable. Now, if I had given you this problem right here and I asked you to solve that, I hope that you would have said without a problem, without any hesitation, oh, well, that's u squared, so naturally we're going to factor this and break down that u squared as u times u, right? And then you're going to look at that constant of 48 to find factors of 48 that subtract to 2. And you would tell me that you would use 8 and 6. Not only that, you would say minus 8 and plus 6. And I'd say, yeah, that's exactly what you do. And then you'd finish using the zero factor theorem. So here, that means u equals 8, or from the other factor, u equals negative 6. But we can't stop here because we didn't start with u. This is now where you go back to what the original problem was. In the original problem we had x, not u. So we have to go back and remember what our substitution was there for. U was just a placeholder. We now want to go back from the u into what it was representing, the 5x plus 6. So I'm not plugging in 8 or negative 6 anywhere, I'm just now rewriting the u for the 5x plus 6. So 5x plus 6 is equal to 8 over here. Likewise, this u was a placeholder for 5x plus 6. And so now we have these two small linear equations to solve. So solving this guy, hopefully you can just kind of do this in your head. Subtract 6 to the other side, you get 2. And divide both sides by 5. X is equal to 2 over 5. And over here, 5x is equal to negative 12 when you subtract 6 on both sides, and then we divide by 5. So we get negative 12 over 5. Okay? So this problem would have been more difficult if we had tried to expand the square and distribute at the very beginning. But by making a substitution, it simplifies the equation. We can use nice, easy factoring techniques to factor, to use the zero factor theorem, and then we go back to what u was representing. And once we do that, we now have two small linear equations for us to solve. Okay? All right. Let's do another one that is very similar to that so that we can do a u substitution. Because these guys, again, it's not just seeing them here in this section, but you see them quite often the deeper you go into mathematics. All right, so I have x to the 2/3 minus 6x to the 1/3 plus 5 equals 0. See, unfortunately, this is not a polynomial equation where we can just say factor it, right? So the first guy that I had, which was, what do we have over here? X to the 4th and x squared. Yeah, we can factor that. We've seen how to factor that before. So we just do it, and we're good. Here, I want you to notice that this guy's quadratic in nature. You've got your constant term. You have some wacky looking variable expression here, and you see something that looks very similar to it here. Notice how these degrees compare, or how the powers compare. This is 1/3, and if you double 1/3, you get 2/3. So this is going to be quadratic in nature. When you make your declaration for u, you're going to let it be this guy here in the middle. Not the 6, but just that variable piece. So let u equal x to the 1/3. And if you do that, then u squared is going to be this guy with double the power. And again, if you double 1/3, you get 2/3. And so we can use these statements to rewrite our equation into something that should be a little bit nicer. All right? So this becomes u squared minus 6u plus 5 is equal to 0. Now, doesn't that look a lot nicer? You don't have those weird rational powers running around. It's just u squared, u, and a constant. So let's see how this factors. Well, again, we have that expectation that u squared becomes u times u. And then when you define the factors of 5, that will add to 6. Well, there's only one way you can break down 5 without doing anything crazy, and that's to use 1 and 5. And again, paying attention to our signs, both of these guys are going to be negative. Okay? So now we're at the point where we use that zero factor theorem. So that means here that u equals 1, or from the other factor, u equals 5. All right. But I can't stop there, right? This is in terms of u. I want this to be in terms of x. Okay, so u is x to the 1/3. But you know what? We just got done talking about this, right? We have a rational power, and the way we undo that is to use the reciprocal. So the reciprocal of 1/3 is 3, and we raise both sides to the 3rd power like that. So this gives me just plain x, and 1 to the 3rd is 1. The same thing's going to happen over here. U is x to the 1/3. And so I'm going to raise both sides here to the reciprocal power, which is 3. And we get plain x on the left. On the right, we get 5 to the 3rd, which is 125. So cool. We get these two solutions. Now, I do want to make sure that you remember something we just talked about a moment ago in this video. When I have x to the 1/3 equal to 5, remember what we said about x to the 1/3. X to the 1/3 really means the cube root of x. So whether you say x to the 1/3 or the cube root of x, they're the same thing. And not only are they the same thing, the way you solve these will be the same. So you know to undo a cube root, you would cube both sides. And again, you would have x is equal to 125. Right? So either way you cut it, you get the same answer. All right, now let's get dangerous. Still using the same concepts as before. Let's try this. X plus 5 over x minus 3 quantity squared plus 5 times that same quantity x plus 5 over x minus 3 minus 24 equals 0. Now, I hope it's pretty apparent to you what's going on. You have the exact same crazy wackadoo variable expression. So that's usually your clue for how you want to define your usage of u for your u substitution. So let's let u be x plus 5 over x minus 3. Okay? So that means we're going to take these expressions here and here, and we're going to rewrite them. So now, that's u, keep the square and the plus 5. That's plus 5 times big fraction, so plus 5 times u. Minus 24 is equal to 0. Okay? Well, it looks like another problem that can factor. So, let's factor this polynomial. We know that u squared is going to break down as u times u. And I do want you guys to remember that while I'm doing this, I don't even care what u is representing right now. I don't care that u is a big fraction. That's not important. What's important is that I'm seeing this as a nice trinomial to factor. That's what's important. That's what I can do. All right, so the way we want to break down 24, find factors of 24, the subtracted 5, it's going to be 8 and 3. So it's plus 8 and minus 3. Again, use that zero factor theorem. So u is equal to negative 8. Or from this guy, u equals positive 3. Just like with the other problems, once you get u by itself, you now make the switch back to what it was representing. U was representing this big fraction. So let's make that adjustment. So this means now x plus 5 over x minus 3, as we make that transition back from the u to the x. This is equal to negative 8. Now, seeing that I have what looks to be a rational equation, I'm going to rewrite the negative 8 as negative 8 over 1. One of the things we talked about in our video yesterday when we were solving rational equations is that when you have a fraction equal to a fraction, that's a proportion, and you can set the cross products equal. So that's what I'm going to do here. That cross product is supposed to equal that cross product. So 1 times x plus 5 equals negative 8 times x minus 3. All right, so that's just x plus 5 is equal to negative 8x plus 24. And now it's just a matter of solving this linear equation. I'm going to move the 8x over to the left. I'm going to move my constant to the right. So that gives me 9x, subtract the 5 from 24, we get 19. Divide by 9, and x is equal to 19 ninths. Okay. Now I'm not going to box that just yet because we have something we need to talk about. We've got to do the same thing for the other half here. Again, that u was standing in place of x plus 5 over x minus 3. And again, I want to write the 3, I want to write that number on the right side as a fraction so that I can recognize that I have a proportion and solve that proportion accordingly. Okay. So we set the cross products equal. All right, so 1 times x plus 5 equals 3 times x minus 3. X plus 5 when I distribute equals 3x minus 9. All right, in this case, I'm going to move my x's, move my variables to the right so that I can have a positive coefficient. So if x goes to the right, then 9 needs to go to the left. So subtracting x gives me 2x on the right side. To move the 9 to the left, I have to add 9, so I get 14. Divide by 2, and x equals 7. Now I told you that I wasn't ready to go ahead and box my answers, because if you look at the original problem, it was a rational equation, and with rational equations, you must be mindful of your restricted values. Okay? So if you come back up here, because we have a fraction, there is that potential to have a restricted value, meaning a value that we can never have as a solution. And that comes from this denominator. The value of x that would make this denominator equal 0 would be when x equals 3. So we could have any number for a solution as long as we don't have x equals 3. So we came up with 19 over 9. So that's not 3, so that's not going to be a problem. And x equals 7. Again, it doesn't equal 3. He won't give us any issues. He won't make us undefined. So both of these solutions are going to be good for us. All right. All right. Let's do one more. Right? Let's go for bonus. Let's take what we've seen so far and just extend it. And what you're looking at is a question that I would like to give as a bonus on an exam. I think students don't think that it's fair that I would give a bonus like this, but bonuses are optional. I hope that you can already see that there's a bit of a pattern going on here, and that you'll be able to see how you want to make a substitution to potentially make this problem a little bit easier to view and work. All right, there we go. Oh man, I'm tired. I was just writing the problem, not even doing it yet. All right. So, as you have probably guessed, this is going to be my u. You see this guy is repeated for these other sections of the problem. And let's see what happens if I let u represent this complicated looking expression. So let's make that transition. So this is now 3 u to the third minus 4 u squared minus 75 u plus 100 equals 0. All right, now that we have it looking like this, I hope it's easy for you guys to see what we should do. Again, the answer for most of this is going to be factor, right? So if we look here, in this first group, we have a common factor of u squared. So factor out the u squared, and we are left with 3u minus 4. In the second group begins with a negative, so we factor the negative out. The common factor for 75 and 100 is 25. So we factor that out. We're left with a positive 3u, and the positive 100 divided by negative 25 is negative 4. Can't really say that I'm surprised here, because if we're going to factor by grouping, these pieces that are left over have to be exactly the same. Otherwise, we either did something wrong or it can't factor by grouping. Okay, so we have 3u minus 4 times what it was connected to, which was u squared, minus 25. Now, we're not even done factoring, because if you look at this carefully, you've got u squared minus 25. And u squared minus 25 is the difference of two squares, so that guy can actually break down a little bit more. So let's go ahead and do that so we can completely factor everything. All right, so 3u minus 4. And now we're going to take care of this guy. So as the difference of squares, it becomes u plus 5 times u minus 5. So even though this is a problem that it wasn't even quadratic in nature, it was a polynomial. Well, polynomial in nature, I should say. We make a u substitution, and it becomes factoring by grouping. And in the factoring by grouping process, there's a difference of squares. And we still haven't even solved for x. We're still dealing in terms of u. So here, solve this guy, and u is equal to positive 4/3. In the middle, you get u by itself, so u is equal to negative 5, and the last factor, u equals positive 5. So we have three different pieces we have to consider. And now we go back to what u was representing. So if you look above, u was representing this fraction right here. So for each of these three pieces, each of those u's will be rewritten with x minus 2 over 2x plus 5. And each of these new equations will form a proportion, and in those proportions the cross products are going to be equal. All right, so let's take care of that. Here, for this cross product, if you want to write it out like I was doing before, you can. If you can do it in your head, that's good too. Just make sure that you distribute correctly and watch your signs. So 3 times x minus 2 becomes 3x minus 6. When you distribute the 4 to the 2x plus 5, we get 8x plus 20. And now we just need to get all the x's to one side, so the best way, I think, is to move the x's to the right and move the constants to the left so that we can maintain a positive lead coefficient. So 3x goes to the right, 5x. Subtract the 20 over here to the left, that's negative 26. Divide both sides by 5, and we get negative 26 over 5. Okay? So really, once we get to this point right here, it's really nothing to worry about. It just goes back to the things we've dealt with before, right? We don't have to worry so much about it being quadratic in nature. We just make that transition back to x, and we solve it. Now, before I box this, let's take a quick look at this expression up here. The restricted value, the one that would make this denominator equal to 0, would be negative 5 over 2. So imagine, if you were to set that denominator equal to 0, subtract 5, divide by 2. So as long as we don't have that as an answer, then we're going to be okay. All right. So now we go to the next guy. X minus 2 over 2x plus 5 is equal to, let's say this is negative 5 over 1, just to make it easier. Set those cross products equal. 1 times x minus 2, that's easy enough, equals negative 5 times 2x plus 5, negative 10x minus 24. And here, I'm going to move my variables to the left to get a positive coefficient. And then my constant is going to go to the right. So I have 11x is equal to, add 2 to both sides. If you need to write plus 2 and plus 2 so that you don't make a mistake, go for it. All right? No need to make careless mistakes. Add the 2 and we get negative 23. Divide both sides by 11. Negative 23 over 11. And then, finally, we take u equals 5. So x minus 2 over 2x plus 5 equals 5 over 1. Let's set those cross products equal yet again. So 1 times x minus 2 is still x minus 2. Positive 5 times 2x plus 5 is 10x plus 25. In this problem, I want to maintain a positive coefficient for x. I'm going to move the x's to the right, which means the constant goes to the left. All right, so x goes to the right. That gives me a positive 9x. Moving the constant by subtracting 25 on both sides gives me negative 27. Divide both sides by 9, and we get negative 3. So the only restricted value that we had in this problem was negative 5 over 2, and we never came across it. He never showed up as one of our answers. So, I mean, this guy's done. That's it. So, what do you think? I know it takes a bit of work, but piece by piece and step by step, we can get there. Okay? Well, that's it for the solving of equations for today. We talked about using the power property. We talked about solving equations that are quadratic in nature and how we make a substitution so that they can then become things that are quadratic and we can factor. Okay? Now, coming up tomorrow, we're going to be talking about solving inequalities, and we're also going to talk about absolute value equations and inequalities. So that should get us through most of the stuff that we have in Chapter 1 in our textbook. Remember, you can always find more of me by going there. Find these videos uploaded on YouTube with timestamps in the descriptions. You can also follow me on Twitch. That's where you're watching right now. Follow me on Twitter for things that are not always math related. Anyway, thank you guys for stopping by. Hope you have yourselves a great evening and a great rest of the day.